Now that we've been introduced to the idea of relative extremum, let's compute some explicit functions here. So I have this function, g of xy equals x minus 1 squared plus y minus 3 squared. So I want to find the extremum of this. And the way you want to do this is, recall we need to take the partial derivatives with respect to each variable. So we want to take the partial of g with respect to x, and that's 2x minus 1, right? And the partial of g with respect to y is 2y minus 3. So what I need to do is I need to find the values for which x and y are. Look, the first thing I want to do, take a step back, is I want to look at this and I want to say, all right, are there any places where these partials don't exist? And the answer is no, because these are both just linear functions. They're equations of lines. So then I have to say, all right, well, where would this function be equal to 0? So if I set this equal to 0, that's at the case where x is 1/2. If I set this is equal to 0, whoops, I apologize, that's x equals 1, 2y minus 6. It's a case where y equals 3. So in these particular cases, x equals 1 makes this one 0, y equals 3 makes this one 0. But I need a point that makes both of them 0. Well, anytime x is 1, this is 0. Anytime y is 3, this is 0. So the point 1, 3 should make both of them 0. So if I take gx 1, 3, I get 2, or 1 minus 1. Notice I didn't even have to plug in the y because it's not here. So I get 0. And then similarly, gy at 1, 3 is 2, 3 minus 3, which is 0. So that tells me that 1, 3 is the critical point. Or it is a critical point. Then I need to take this and plug it back into here to find the relative extrema, because when we're plotting this, we have both the input variables and the output variable. So if I plug 1, 3 in here, if I plug 1 into this, it's 1 squared is 0, or 1 minus 1 squared is 0, 3 minus 3 squared is 0. So my point is actually 1, 3, 0. So that was a lot of work there. And I want to point out something. We didn't actually have to do the calculus here. Think about this function for a second. I have something squared plus something squared. Well, if this wasn't x minus 1 or y minus 3, if that was just g of xy equals x squared plus y squared, that would be like z equals x squared plus y squared, which would be that elliptic paraboloid. Well, the elliptic paraboloid looks like a parabola, so there's a bowl that comes all the way to the bottom, and there's just one small minimum. And this is just a shifted version of that, shifted over 1 unit, shifted over 3 units, and the bottom's at 0. But even if we didn't understand it was a paraboloid, there's a third way to do it, and that's by looking at this algebraically. Think about this. If this is any number but 1, then this number can't be 0, and when you square it, it's positive. When this number is anything but 3, this number isn't 0. When you square it, it's positive. So no matter what, if this isn't 1 and this isn't 3, the output of the function is larger than 0. But it can never be any less than 0 because these things are squared. So that tells me, no matter what, that the minimum has to be at 1, 3, and then the output of the function will be 0 when I plug it in. So you can use calculus, or you can use a little bit of algebra and mathematical intuition to keep you from working harder than you have to. So let's keep that in mind as we move over here. So I could take the partial derivative here. I could say fx, xy That's my partial derivative. And my partial derivative here is there. Now I want to check and see where this function doesn't exist. Well, no matter what I plug in for x or y, those will be at least 0, if not positive. So the bottom, there's never a negative in the square root, and it's never 0. So for practical purposes, these are kind of non-issues, and x and y are perfectly defined everywhere. So we don't have any critical points where the function's undefined. So then I would say, okay, well, where is this equal to 0, and where is this equal to 0? Well, if x is 0, then the rest of it's 0. If y is 0, the rest of it's 0. So that tells me that the point 0, 0, and if I plug that in, 0 squared plus 0 squared plus 1 is 1, square root is 1, is my relative minimum. And the reason I know that it's a minimum is, again, let's look at this. No matter what I plug in for x, if it's not 0, it'll be positive. If it's not 0, it'll be positive when it's squared. So no matter what I plug in for x or y, if it's not 0, that's going to be added to 1, which makes it larger than 1, and the square root keeps it larger than 1. So the minimum has to occur at 0, 0. And again, it's a minimum because there's no way to get any value of the function that's lower than 1. So let's keep that in mind as we keep moving forward here. So I have this function, I say, okay, well, this is not set up with any, I've got some squareds, but I've got some other change. So there's not an easy way to do it. Well, let's go ahead and take a partial derivative and see. Two x plus 2, partial derivative with respect to y, 2y minus 6. So then what I'm going to do is take a look at these and say, okay, well, when x is -1 and y is 3, well, then that works. Then that's some function. And then if I plug 1 and -1 and 3 in here, I get 1 plus 9 is 10, minus 2 is 8, minus 18 is -10, it's -10, plus 6 is -4. And then you might say, well, is it a maximum or a minimum? And there's a couple of ways to do this. The easiest way is, if you only have one critical point, is to just plug like 0 in. So if I plugged in 0 for this function, I would get, or the 0, 0, I get 0, 0, 0, 0, 6. Well, 6 is larger than -4, so that tells me it's a minimum. That's pretty unscientific way to do it. When you have a bunch of critical points, that's not a good way to do it. But if you only have one, it's not a bad way to do it. Another way to do this is, again, let's use some algebra. Let's do some factoring here. So let's take a +1 plus 9, so that's 10, but we have to get to 6, so -4. I have to, that way it all works out. So then that is x plus 1 squared plus y minus 3 squared minus 4. Now that I have this, I have something that looks a whole lot like what I was dealing with over here. And I can use the fact that I know these are squareds to say, okay, well, when these things are equal to 0, that's my minimum. And then that -4 tells me what the value of the function is at that minimum. So the calculus is important, and there's going to be plenty of functions that you can't just sort of cheat your way through. You're going to have to do it, and that's why we want to do it here. But I also want to emphasize, just don't work harder than you have to. Time and again, working smarter, not harder, is going to get you way further, not only in math, but in life.